Okay, so we're going to go through this last problem here, which is when you deal with trig and implicit differentiation. And what you have to remember is implicit differentiation is really just an extension of the chain rule. So without further ado here, we're going to actually do this. So if I want to find dy dx, the first thing that's important is remembering that that's dx. I'm taking the derivative with respect to x. So I'm going to take d dx of cotan x plus y and d dx of x on the other side. And so to actually do that here, the derivative of cotan x plus y would also be a chain rule. So I'm going to take the derivative of the outside, which would be negative cosecant squared, keep the inside, times the derivative of the inside. Now the derivative of x with respect to x is just 1. The derivative of y with respect to x is also 1, but I also need a dy dx because I'm taking the derivative with respect to a different variable. So it's 1 dy dx or just dy dx. And then the derivative of x is just 1 on the right-hand side. So I'm supposed to solve for dy dx, so I want to get my dy dx guy alone. So I'm going to divide both sides by negative cosecant squared. And when I do that, I get 1 plus dy dx equals negative sine squared x plus y through the powers vested in me and the properties of trigonometry, because the reciprocal of cosecant would just be sine again. And then I'm going to subtract 1 from both sides, giving me negative sine squared x plus y minus 1. So there's the derivative. And then I'm supposed to evaluate that at the point pi over 2, 0. So dy dx at the point pi over 2, 0 is going to be negative sine squared pi over 2 plus 0 minus 1. And that's going to be negative 1 minus 1, which is negative 2. Yay! Okay, so I've evaluated it, yay. What does that mean? Well, normally it means that that is the slope of the line tangent to this graph. Notice I said graph and not function. The line tangent to that graph at the point pi over 2, 0. What I didn't check on, though, is the fact that actually this is meaningless. Which seems like, wait, seriously, Mrs. River, why did you make us do that? I didn't make you do anything wrong. We followed the instructions. We did what we were supposed to do. We got an answer. It's just that that answer is meaningless in the context of being the derivative of this. So let me show you what I mean. So if I come over here, these red lines are the graph of cotan x plus y equals x. Okay, obviously not a function. It's funky. Looks kind of cool, but it's not a function. And then right here is the point pi over 2, 0. That point is not on the graph. So I can plug that point into the derivative. It just doesn't mean anything. Okay, so the thing about implicit is you can evaluate implicit derivatives at tons of points, but it might have no meaning for the equation that you're actually evaluating. So let me give you an idea of what I'm talking about here. If we come back over to here, it says find the points at which this has a vertical tangent line. So in this graph, I think we had dy dx equals like 4 minus 4x over something over y plus 2. And this question asked for a vertical tangent line. So we said there's going to be a vertical tangent line when y plus 2 equals 0. Which happens at y equals negative 2. And then if you remember, I plugged this negative 2 back into here, okay? And I ended up getting the points, hang on, I'm looking it up here, 0, negative 2, and negative 2, negative 2. So these are locations where there was a vertical tangent line, okay? What if, though, if you look back on your notes, which you probably have in front of you here, what if instead of that, I had something like, when we got down to the end of it, we had like 4x squared minus 8x equals 0. What if instead of that, Instead of that, what if my original function, instead of being set equal to 0, was set equal to like -20? It wouldn't have affected the derivative, but it would have all of a sudden made this a -20. And then when I go to solve this equation, I wouldn't get an x. I wouldn't get a real x. I'd have nothing. So I guess my point is, and I'm not here to explain it to you, but I guess my point is, when you do these implicit derivatives, you're going to get a derivative, and there's nothing wrong with your derivative. But if you use this to find other values, you have to make sure those other values are actually points on your curve. I promise I'm never going to trick you. I'm not going to say find the tangent line and then give you a point that doesn't work. But I may say things like, if any horizontal tangents exist, find their equation. Okay? So I'm going to stop talking now. Your homework is up on the board in orange. You're going to do the review questions first and then the exercises, and check your answers in the back of the book. Your homework has been reminded to you via the text app, or it's on my website and says video number 2 under implicit. So yeah, there you go. I'm done. Since this is a video, I guess you need a joke. I'm on this new thing now, and it gives me nerdy dad jokes. And so the nerdy dad joke that came across my desk this morning was, hey, do you want to hear a joke about paper? And never mind, it's terrible. Get it? Terrible. T-E-A-R, terrible. Like you can rip paper in half? Ha ha ha. I know it's terrible, but it's a dad joke. All right, enjoy your day. Do your homework. See you tomorrow.